Welcome to Notes 15.6, Part 2. We'll begin Part 2 with Example 6 on page 4. Example 6 says to find the equation of the tangent line to the curve of intersection of two surfaces at a particular point. In order to understand how we're going to approach this problem, let's take a look at what these surfaces look like. Again, in GeoGebra, we can graph both surfaces, and we see that one surface is a paraboloid and the other surface is a plane. And we can see the point at which we want to find the equation of the tangent line to the curve of intersection. Now we can see from this model that the curve of intersection looks like an ellipse, and we want the equation of the line tangent to the ellipse. Here's what I know. I know the line tangent to that ellipse lies in the tangent plane to that ellipsoid at that point and in the given plane that it's intersecting with. That means the direction vector for that tangent line must be orthogonal to both the gradient of the paraboloid and the gradient for the plane. So in order to find the direction vector for the line, that's what we're going to do. We're going to find the gradient for the paraboloid, find the gradient for the plane, do the cross product in order to find a direction vector orthogonal to both of those, and that'll be the direction vector for our line. Let's give it a try. Let's begin with the equation of the paraboloid. Our first step will be to rewrite this in the form capital F equals 0. Next, we'll find the gradient of this capital F, and we'll evaluate that gradient at the given point. So far, so good. Next, let's examine our other surface, the plane z equals 4 minus y. Again, let's set it equal to 0, and this time I'll call it capital G instead of capital F. And again, let's find the gradient. We don't have to evaluate it at the given point because this gradient is a constant vector. Now our plan will be to find a vector that is orthogonal to both of these gradients. A vector orthogonal to both of these should be a vector in the direction of the tangent line. Let's go ahead and compute the cross product of this gradient for F and gradient for G. Computing the cross product using the determinant, as we learned in an earlier section, we get that the cross product of these two vectors is 1, 4, negative 4. Again, this vector will give us the direction vector for our tangent line. Now all we have to do is write the equation of a line that passes through the given point 2, negative 1, 5, and has direction 1, 4, negative 4. So the equation of our tangent line is r of t equals the vector 2, negative 1, 5 plus t times the vector 1, 4, negative 4. All right, let's go on to the next page. We now turn to an application of tangent planes, linear approximations. Recall that we used linear approximations in Calc 1 and 2 to approximate the value of a single variable function near a particular point. It makes sense then that in space, a tangent plane might be used to approximate functions of two variables. From Calc 1, we can write the equation of a tangent line to a function y equals f of x at a point a, f of a. The value on the tangent line, we'll call it y sub t, is an approximation to a value on the actual function f of x. And that y of t value is simply your slope, f prime of a, times x minus a, plus f of a. This is nothing more than the point-slope form for the equation of a line. We can extend this to our two-variable situation with z equals f of xy at the point a, b, and f of ab. Thus, the linear approximation using a tangent plane is given by L of xy, and again, that's an approximation to the actual function value. And we take the partial of f with respect to x evaluated at ab times x minus a, plus the partial of f with respect to y evaluated at ab times y minus b, plus f of ab. Note that this is just the equation of the tangent plane that we had earlier in our notes. So a linear approximation is simply an equation of a tangent plane. Let's take a look at example 7. Find the linear approximation to the given function at the point 1, 2. And then we're going to use it to approximate the value of the function at a point close to 1, 2. Again, the linear approximation is simply the equation of the tangent plane. So first we'll need our partial derivatives. Partial of f with respect to x is negative 8x, and partial of f with respect to y is negative 6y. Now we'll evaluate the gradient of f, which just consists of those partials, at the point 1, 2 to get the actual values at our given point. And when we substitute in the point 1, 2, we get that our partial of f with respect to x is negative 8, and with respect to y is negative 12. Now we'll use those to write the equation of our tangent plane. To write the equation of our tangent plane, we'll need one more thing. We'll need to know what is the z value at the point 1, 2. In other words, what is f of 1, 2? Well, to find that, we just plug 1, 2 into the given equation. And working that out, we get negative 6. Now we're ready to write the equation of our tangent plane. Using the same process we used earlier in the notes, the equation of our tangent plane, L of xy, or you could say z sub t equals negative 8 times x minus 1 minus 12 times y minus 2 minus that f of 1, 2 value, or rather plus that f of 1, 2 value, which is negative 6. Now this problem does ask for something else. It asks us to approximate the value of the function at 1.1, 1.99 using our linear approximation. All we have to do for that is plug in these new x and y values to that linear approximation, that tangent plane equation. The function value at 1.1, 1.99 will be approximately equal to the value on the tangent plane. Substituting those values in and working it out, we get that f of 1.1, 1.99 is approximately negative 6.68. That's the approximation on the tangent plane. In other words, that's the value on the tangent plane, which should be pretty close to the value that we would have on the actual surface. Just to check, I did go ahead and compute the actual value on the surface. That actual value is negative 6.72. So we can see that our linear approximation is pretty close. And that'll be the case as long as we're using it to approximate a function value near the point of tangency. All right, let's go on to the last part of these notes, increments and differentials. Again, these are topics you had in Calc 1. You had equations of curves, and then you did tangent lines. You did linear approximations, which was just using tangent lines. And you may or may not remember, but you also did differentials, which was just approximating changes in x or y using the tangent line. So we're just extending that idea, but using tangent planes. Recall from Calculus 1 that if you're given y equals f of x, the differential of y is just denoted dy, and the way to compute dy is to use the equation dy equals f prime of x dx. Now the increments of x and y are given by delta x and delta y. When we're computing the differential of y, we allow dx to equal delta x. Let me show you what this looked like in 2 dimensions back in Calc 1. Back in Calc 1 again, we learned that if we had a function, that's what I have in blue there, to get from one point to another, you had delta y and delta x, the change in y and the change in x. If you had a tangent line at a particular point, then the slope of that tangent line was dy dx, meaning a small change in y was dy and a small change in x was dx. If we make our dx the same as our delta x, we can see that our dy value is not exactly the same as our delta y value, but it's pretty close nonetheless, as long as our dx is not very large. So we can use dy as a means of approximating delta y. Now back to our situation in space. In space, we'll be able to use our dz to approximate our delta z. So first, what is delta z? Well, delta z is the actual change in the z value as x and y are increased by delta x and delta y. But we're not going to actually compute delta z very often. Instead, we're going to approximate delta z by computing dz. And we're going to do that by defining something called the total differential. The total differential of the dependent variable z dependent on x and y is given by dz equals partial of z with respect to x times dx plus partial of z with respect to y times dy. It looks an awful lot like the chain rule that we had in our last section. This value, dz, represents an approximate change in the z value for given changes in x and y. Also note that we could extend this definition to functions with even more independent variables. Let's begin by just practicing how to compute this total differential. Example 8. Part A, compute the total differential for z equals x cosine y plus e to the xy. This z is our f of xy. So the formula, dz, would be the partial of f with respect to x dx plus partial of f with respect to y dy. Go ahead and take a moment to compute what this total differential would be. Don't worry about simplifying, just get it computed. Compute your partial of f with respect to x and partial of f with respect to y. Pause the video while you do that, and then restart the video once you've got it to check your work. Okay? Pause now and figure out the dz. All right, welcome back. Hopefully you got the same thing I did. My partial of f with respect to x was cosine y plus y e to the xy dx, plus my partial of f with respect to y was negative x sine y plus x e to the y dy. That's it. That's all the total differential is. We'll use it in a minute. Right now we're just practicing finding it. Okay, let's do one that's a little bit more complicated. Let's look at letter B. In letter B, my w is really an f of x, y, z. So that means to find my total differential dw, I need to compute the partial of f with respect to x dx plus partial of f with respect to y dy plus partial of f with respect to z dz. Once again, I would like you to pause the video and work out these different partial derivatives. This one's a little more complicated because you may have things like quotient rule that you need to deal with. So pause the video now and restart it once you've figured out all of your partial derivatives and have your expression written for dw. Pause now. Okay, welcome back. Take a look and see if you were able to find all your partial derivatives correctly. If you made any mistakes, go back and check your work. And if you believe I may have made a mistake, which of course we always know is possible, then let me know. All right, let's go on to the next page and use these total differentials. Example 9. Use the differential dz to approximate the change in z as xy moves from the point 1, 1 to the point 1.01.97. Compare the approximation with the exact change in z. All right, first let's define how we find dz. dz would be the partial of z with respect to x dx plus partial of z with respect to y dy. Okay, go ahead and take a moment and write that down. Pause the video, get that written down, and then restart the video when you've got it. Pause now. All right, welcome back. Hopefully you were able to get the same values that I got. All right, now let's write down a few of the values that were actually given in this problem. First, we're going to need to know the point. We're starting at the point 1, 1, but I'm not given the z value. So let's start by substituting 1, 1 into my z function, and we find out that our point is 1, 1, root 2. Now, in order to compute our differential for z, we're going to need to know our dx and our dy. So let's write those down. Our dx will be 0.01 because we're moving from x equals 1 to x equals 1.01. So the difference is 0.01. Our dy is negative 0.03 because we're moving from the point y equals 1 to y equals 0.97. So the difference is negative 0.03. Plugging in our x and our y and our dx and our dy, we obtain dz equals a whole bunch of stuff that I've written down for you there, which is approximately 0.014. Now, I didn't write it in here, but I did go ahead and compute the actual change in z by finding the function value at 1.01.97, the function value at 1, 1, and subtracting. And when I did that, I got that the actual change in z was 0.0137. So 0.014 is not a bad estimate for some pretty easy work. Note that when we are computing this differential, we're really just finding the difference in the z values on the tangent plane. That means that we could have used the linear approximation method, which is based on tangent planes, to find the new function value at 1.01.97 and subtract the original function value, and that also would have given us the 0.014. Okay, one more problem. Example 10. We're back again to pressure, volume, and temperature of the mole of an ideal gas related by the equation PV equals 8.31 T. Use differentials to approximate the change in the pressure if the volume increases from 12 to 12.3 liters and the temperature decreases from 310 to 305 Kelvin. So the change in the pressure, delta P, can be approximated by finding dP. We're given that the volume is 12, but the change in volume is 0.3 because volume increases from 12 to 12.3. We're given that the temperature is 310 and the change in temperature dt is -5 since temperature decreases from 310 to 305. We also know the equation PV equals 8.31 T, and we can rewrite that as P equals 8.31 TV to the -1. Okay, now let's figure out what our dP would be, our differential for pressure. Using the chain rule, the definition of total differential, we have dP equals partial of P with respect to V dV plus partial of P with respect to T dt. Now we'll substitute in what those quantities are, and we've got our equation for dP. Then we can substitute in all the values we have to compute a value for dP. Substituting all those values in, we get that dP is -8.829 kilopascals. Again, that's an approximation to delta P, the actual change in pressure. Okay, this concludes notes 15.6. Once you've reviewed these notes and feel comfortable, then go ahead into my math lab and start homework number 18.